I want to wrap up the method of undetermined coefficients by looking at what problems can be solved by using this technique that we've been studying. And the general problem for second order would be a2 y double prime plus a1 y prime plus a0 y equals to q of x. And where we have constant coefficients, a2, a1, a0, second order, and it's non-homogeneous. The right-hand side is a function of x. Now the book that I've been working out of also does higher order equations using this technique. It has a few third and fourth order equations, and I've shied away from those because I don't know of specific examples in the real world that uses anything higher than a second order differential equation. They may be out there, I'm just not aware of them. But I think this being an introductory course in differential equations, it suffices to me to study the second order. But you can generalize this to higher order if you want to. Okay, now in the non-homogeneous case, we have only been playing with these kinds of functions. We've been playing with functions that look like e to the x, exponential functions. We've been playing with polynomials. And we've been playing with sines and cosines. That's pretty much it. Okay. Now we can add a few more functions to this list, and I'll do that in a moment. But the reason that this technique is working for us is because if you take an unlimited number of polynomials, an unlimited number of derivatives of any function on this list, then you'll get another function on that list. And that includes multiplying them together. So we can have a polynomial times e to the x times a sine function. And if we start taking derivatives, we're going to get something that uses these functions. In other words, we never stray outside this list when we take derivatives. And that's important. That means that all the derivatives are called linearly independent, and that's a term that I don't want to spend too much time on. It's something that if you take a linear algebra course, you'll study that in a lot of detail, and all this is sort of related to vector spaces and bases and things like this. Some neat stuff that you study in another course. But that's the idea, that anytime I take these functions, or I can mix them together by multiplying them together if I want to. No matter how many derivatives I take, I still stay on this list. We could add a few more. For example, we could add the sinh and cosh functions. Because these two hyperbolic functions, the derivative of sinh is cosh, the derivative of cosh is sinh. And so their derivatives stay within this list. You can even add a power of sine or cosine. For example, there's a problem in the book. I think it's number 24 on page 231. Let's look at page 231, number 24. The right-hand side is sine squared of x. Well, their hint that they give is to use the identity, the half-angle identity for a sine function. This is 1/2 minus 1/2 cosine 2x. And so we could rewrite sine squared as something that would come off this list. And all these derivatives will stay within this list. So it looks to me like you could really theoretically do that with any power of sine or cosine that's an integer power, and keep it on this list. Alright, so what's the problem with something that's not on our list of approved functions? Now, why can't we use this method of variation of undetermined coefficients? Suppose, for example, that q of x was, let's make it the square root of x. And that's x to the half power. So, for example, if you let your particular solution be ax to the half power, then the first derivative is going to be 1/2 ax to the minus 1/2, and the second derivative is going to be minus 1/4 ax to the minus 3/2. And so we end up with a real problem here. We start creating new functions that are not on this list. I mean, if I had square root of x on this list, its derivatives do not appear on that list. And if I put those up there, further derivatives are going to introduce yet more different functions not on our list. And so there's a problem. If q of x was equal to the tangent of x, well, the derivative of tangent is secant squared. The derivative of secant squared is something more complicated, and it just keeps getting more complicated, and you don't end up staying on this list. so there's, those kinds of functions do not lend themselves to the technique we've been using, the method of undetermined coefficients. So we're kind of stuck there. But there is a technique that will allow us to solve some of those problems. It's called the method of variation of parameters, and we're going to study that next.